The concept that our universe might be a mere membrane, or brane, floating in a higher dimensional space is one of the most revolutionary and mind-bending ideas in modern theoretical physics. It challenges our fundamental understanding of reality, suggesting that the three dimensions of space we experience are not the whole story, but rather a three-dimensional surface embedded in a larger, invisible bulk of higher dimensional space. This is the central premise of the Braneworld Theory, a framework that has captivated physicists and the public alike, offering elegant solutions to some of the most perplexing problems in physics, such as the hierarchy problem, the vast discrepancy between the strength of gravity and the other fundamental forces. To make this abstract and mathematically complex concept accessible, physicists have turned to a surprisingly apt analogy: Lewis Carroll's Alice's Adventures in Wonderland, a world where size, scale, and perspective are fluid and fantastical. The Alice in Wonderland Analogy, as popularized by physicists like Raman Sundrum, co-author of the influential Randall-Sundrum model, is a powerful tool for visualizing the warped geometry that lies at the heart of the brain world. In this thought experiment, you are Alice, standing in a room. You walk to one side, and your head crashes into the ceiling. You walk to the opposite corner, and you shrink to the size of an ant. Your apparent size changes simply by moving from one place to another. This, Sundrum explains, is what it feels like to be in curved space, and it illustrates how your apparent size or length scale varies as you move across a warped dimension. The Alice analogy is not just a whimsical comparison. It is a direct metaphor for how a warped extra dimension could resolve the hierarchy problem. The problem arises because the mass of the Higgs boson, and by extension the scale of electroweak interactions, is about 10 to the power of 16 times smaller than the Planck scale, the fundamental scale of gravity. This vast discrepancy is unnatural in particle physics, requiring a seemingly arbitrary fine-tuning of parameters. The warp geometry of the brane world solves this by creating a warp factor that exponentially redshifts the fundamental scale of gravity down to the electroweak scale on our brain. In the Randall-Sundrum model, two branes are placed at the boundaries of a compact fifth dimension. The geometry of the bulk spacetime is warped, creating a natural hierarchy of energy scales. The value of the warp factor, determined by the product of the curvature scale and the size of the extra dimension, is about 10 to the power of negative 16, exactly the factor needed to explain the hierarchy. This is the mathematical equivalent of Alice's size changing as she moves through Wonderland. The history of the Braneworld concept is rooted in the mathematical demands of string theory. In the 1990s, physicists following developments in string theory realized that it seemed to require more dimensions than the three spatial dimensions we experience. In the traditional Kaluza-Klein picture, these extra dimensions were compactified, or curled up, on fantastically small scales. The Braneworld scenario offered a radical new perspective. Instead of being compactified, at least one extra dimension could be relatively large, perhaps even infinite. We, and all the particles of the standard model, are stuck on a three-dimensional brane, a surface embedded in this higher dimensional bulk. Gravity, however, is not confined to the brane. It can propagate throughout the bulk. This elegant picture explains why gravity is so much weaker than the other forces. Its strength is diluted as it spreads through the extra dimensions of the bulk. As Sundrum explains, we were contemplating the idea that we, the particles we're all made of, and all of our atoms are stuck on a three-dimensional plane in a higher dimensional bulk, and even photons of light are stuck on this surface. The non-gravitational forces are trapped on the brane, while gravity is free to roam in the higher dimensional space. The intellectual lineage of the Alice analogy in physics extends beyond the brane world. In 1965, physicist Jean-Marc Lévy-Leblond discovered a new non-relativistic limit of the Poincaré group, which he named Carrollian spacetime, after Lewis Carroll, the author of Alice's Adventures in Wonderland. He noted that the absence of causality and the arbitrariness of time intervals in a universe governed by this symmetry were reminiscent of the chaotic and illogical world Alice finds herself in. This historical connection highlights the deep and enduring link between the abstract, counterintuitive world of theoretical physics and the fantastical, logic-defying world of Wonderland. It suggests that the physics of the very small and the very large can be just as strange and wonderful as the adventures of a curious girl who fell down a rabbit hole. The Braneworld idea has also been linked to the possibility of wormholes and travel between parallel universes. Wormholes, theoretical shortcuts through space-time arising from Einstein's theory of general relativity, could potentially connect different regions of the same universe, or even different branes in the bulk. It is possible that a wormhole, perhaps at the center of a rotating black hole, could allow bits of matter or energy to slip from one universe to another. This has even been proposed as a possible resolution to the black hole information paradox, where information that enters a black hole might exit into a parallel universe. This speculative idea, while far from established, resonates with the concept of parallel universes that is a staple of science fiction and popular culture. It raises the tantalizing possibility that our universe might not be alone, but one of many, with the Braneworld providing a plausible framework for such a multiverse. The Alice analogy is also used to describe wormholes themselves. In fiction, the rabbit hole is a classic example of a wormhole, a portal to another world, and the idea of a shorter path through spacetime is central to the concept. The cosmological implications of the Braneworld scenario are profound. In the traditional view of cosmology, our universe is a self-contained, four-dimensional spacetime. In the Braneworld picture, our universe is a brane embedded in a higher-dimensional bulk. This fundamental change in the structure of spacetime has dramatic consequences for the evolution of the universe, particularly in its earliest moments. The modified Friedmann equation, which governs the expansion of the universe, acquires new terms that become significant at high energies, potentially altering the dynamics of inflation and the generation of primordial perturbations. The Braneworld scenario also offers new possibilities for understanding dark energy and the late-time acceleration of the universe. For instance, the Dvali-Gebedadsparity (DGP) model, another Braneworld model, modifies gravity at large distances, providing an alternative explanation for cosmic acceleration without invoking a cosmological constant. The search for evidence of extra dimensions and braneworlds is an ongoing endeavor at the frontiers of experimental physics. The Large Hadron Collider, LHC, at CERN is one of the primary tools for this search. If extra dimensions exist, they could leave a detectable signature in the debris of high-energy particle collisions. One potential signature is the production of Kaluza-Klein modes, which are heavier versions of known particles that carry momentum in the extra dimensions. Another possibility is the production of gravitons that escape into the bulk, creating a missing energy signature. However, despite years of searching, the LHC has not yet found any evidence of extra dimensions or new particles that would confirm the Braneworld scenario. As Sundrum acknowledges, the real question is whether nature chooses to use this framework or something else entirely. The lack of observational evidence does not necessarily mean the theory is wrong, but it may mean that the extra dimensions are at scales that are currently beyond our experimental reach. The Braneworld Theory, with its Alice in Wonderland analogy, is a testament to the power of the human imagination to conceive of realities beyond our direct perception. It is a framework that challenges our common-sense notions of space, size, and the nature of reality. The idea that our universe might be a membrane in a higher dimensional space, where the laws of physics are shaped by warped geometry, is as fantastical as anything Alice encountered in Wonderland. Yet, it is a serious scientific hypothesis, one that has the potential to resolve some of the deepest mysteries in physics. The Alice analogy is not just a clever pedagogical tool. It is a reflection of the inherent strangeness of the universe at its most fundamental level, a strangeness that is every bit as wondrous and disorienting as a tea party with the Mad Hatter. As we continue to explore the cosmos, both with telescopes and particle accelerators, we may one day find that reality is indeed far stranger and more wonderful than we could ever have imagined, and that Alice's adventures were, in some sense, a premonition of the universe we are only just beginning to understand.